All right, Chapter 11, Section 4, Congruence and Transformations. This is the culminating section here in Chapter 11 on transformations and kind of the point as to why we even bother with these multiple transformations, namely the rigid motions in this chapter in Math 1. So first, just to break down the title, Congruence. I've described this in class before. Congruence is a very deep type of definition. And the way I described it to you guys is that two objects can have a single dimension that is equal, right? And there's a big confusion, a common misconception that congruence means two things are equal. Well, equal is very specific, all right? For instance, if just like in our previous sections, if I were to use our protractor, if I were to take a ruler out and measure the length of this side of the protractor, and then take an identical protractor and measure that length again, they could have two equal lengths right there. That is a specific measurement of one-dimensional type of measurement. And equality deals with one dimension. Congruence deals with all the dimensions. And what I mean by that is that, yes, I could measure this length right here and compare it to another protractor, but then I could also measure the height of it or the width, or I could measure how far it was from this little center T junction to one of these numbers. And any one of those individual measurements, the width or the depth of the protractor itself, or anything about it, any of those measurements, when two objects are congruent, every last measurable aspect of one is identical to the other. And that becomes very, very important, particularly when it's a complex object. The more complex, the more useful that property. When it's just a segment being compared to another segment, there's really only one way to measure a segment, and that's its length. And so it's very easy to say that they're congruent because they have the same length, over and done. But when I start getting more complicated, like into shapes like triangles or quadrilaterals, or even something as complex as our protractor, as these things get copied and pasted places, it's very valuable to have that information. Okay? And so congruent figures. Two figures are congruent if and only if a rigid motion or composition of rigid motions maps one figure onto the other. So this is where it kind of uses our previous three sections. Basically, if I were to say take this orange triangle and compare it to this other orange triangle, they're congruent if and only if I can do some composition, some series of movements to get this guy onto this guy so that it completely maps one onto the other. I'm not talking about overlapping or anything like that. Just one point goes exactly to one point in each of the cases. Okay. Now, this is a little less restricted way to prove congruence than, say, measuring every single element of this. Yes, I can go about saying like, well, that's 2 units high, that's 3 units long. I could even use Pythagorean theorem to find the length of that hypotenuse, that side right there, that diagonal, and then compare it to the 3 right here. That would be another way to show congruence, and that's something we're actually going to get into in the next chapter. This one's a little less restricted if I can basically move this piece, this block, onto that guy. This may actually sound familiar. This is something my 1-year-old does when he has blocks. All right, and many of you have seen this child's toy before, where you have some shape of a hole in an object, and then you have a similar shaped block that you have to orient and rotate or move in some way so that it goes through that hole. And only the correct shape will go in that hole. Right? Yeah, this is exactly like that little kids game, and that's pretty much what that is based off of. This idea of transformations. Again, dealing with our 3 transformations, being translation, where I slide some object left, right, or up, down. Whether it's reflection, where it would reflect over a mirror, taking on a mirror image, and then rotation, where I would take an object and rotate it about some center of rotation, some center point. Okay, and so in this example right here, I have 3 different pairs of colored objects. This is not meant to be over challenging. This is just meant to kind of demonstrate how each of these colors can map one onto the other using different transformations. Each of these transformations can be done in a single move, there are ways I can create examples where it takes multiple moves, and that will be a problem that we deal with in our example down here. But for right now, let's just talk through this. Here I have a pink rectangle, okay, quadrilateral, and I can map this quadrilateral onto that one using translation. Basically, if I were to move this corner point to that corner point, the rest of the figure would map onto the rest of the figure. Okay, so here's where I need to be careful, because a very common thing people might mess with is like, all right, well, I can just move that corner down to that guy. No, because I want the whole shape to fit inside that other block, right? So corresponding pieces have to map onto each other. So that top left corner has to map onto the top left corner. How far does it have to go? It would have to go 2 to the right and then 2 down. So just like in section 1, I can describe that transformation with a little coordinate transformation where I would say xy goes to x plus 2, y minus 2. Or I could use the vector with those little angle things, and then I'd have positive 2 and then negative 2 as my vector, mapping this guy onto that one. Okay. And then for my orange triangles, it might be easy to see that I'm just reflecting that over this x-axis when y equals 0, where this corner gets mapped to that corner, that corner, that corner, and that last vertex over here. The green one can be a little trickier to see. Some people would mistakenly think that this is reflected over some diagonal. That's not the case. We can actually see how this corner right here is a little bit stretched out. Notice that that stretched out corner ends up pointing up over here as opposed to pointing down. This is an example of rotation where I would take that piece, and so like if I were to look at my pencil pointing down, right, pointing down kind of like the stretched out piece, as it rotates, notice that the point starts changing its direction, so that ultimately after 180 degrees, now it's pointing that way. This is an example of a rotation on those green triangles. And just to refer back to the solution sheet where I break this down, one thing you'll be asked to do in certain cases is to describe the transformation. You've probably seen this in your section 1, section 2, and section 3 assignments. So pink rectangle to pink rectangle is this translation I described before, x plus 2, and then that should be x or y minus 2. I left out the little minus sign right there. Might as well fill that in while I have the opportunity. There we go, minus 2. All right, the orange triangle was a reflection over this x-axis. Also can be described as the line, horizontal line, y equals 0. And finally, just like we just described, this green triangle can be rotated 180 degrees about the origin, mapping this little shortcut, but we can see that it got halfway to where it could have been if it kept going. All right, so our next example, hint, hint, you may see this on a final, on some sort of assessment in the future that deals with this chapter. This is a very common type of thing. You're going to be shown a starting line, basically, some starting object, in this case a quadrilateral. This is a parallelogram, in case you're wondering. I'm not going to deal with that until Math 2. But ABCD represents some four-sided figure. And I'm going to start here and somehow map it onto this guy, EFGH. Okay, there's a big hint given in how it's phrased. We're going to describe a congruence transformation. Basically, we're just going to describe a series of steps to get this guy moved in some way to go into there. So if we want to think of this like that little child's game, here's our block, and we're trying to move it in some way, shape, or form to get it into this hole. Now, this can be deceiving because with child's blocks, particularly with like this shape, I could put it in one of a couple different ways as long as I can get this longer diagonal side into that longer diagonal side. But what's more important with a congruence transformation, I want to make sure I get a certain point mapped to its corresponding point. Here's what I mean by that. And here's the big hint that was actually given in the phrasing of this word problem. They tell us the name of the figure, ABCD. That's on purpose. This order actually ends up mattering. The first letter A is going to map to the first letter in this guy. This is the image, E, F, G, H. A is going to map to E. B is going to map to F. C to G, and D to H. So looking at my figure, I have to somehow get A into E's position. And I can do that lots of ways, but I have to do it in some way that the rest of the letters end up on where they should be as well. And so it can help to kind of think of it in terms of 2 letters at a time, because if 2 fall into place, the rest are probably going to fall into place as well. But if I can get A onto E, I need B to go to F. B needs to go to F. So see how A has a shorter path than B, so there's going to be some sort of reflection that happens in the process, because I need to flip this side over here onto the other so I can slide it in. All right, so let's move to our solution sheet to talk through this. Now, for the record, for these kinds of problems, there are multiple ways to do it. And that means that there are multiple correct ways to do it. Okay, so this is one of those correct ways to do it. And here's that little note here that I was just describing, this idea that I have to map each of these letters to its corresponding piece in its image. So A goes to E, B to F, C to G, D to H. All right, so there are multiple ways to do it again. This is just one of the ways. I described my first motion being a reflection of this object, my block, over the y-axis when x equals 0. There's my y-axis. If I reflect it over, A goes to A prime, D goes to D prime, C to C prime, so on and so forth. Okay, so there's my reflection over my y-axis, and then next thing I'm going to do is a translation. Okay, and I'm actually just noticing I made a mistake right here. These two should be swapped. See, if I'm reflecting this guy over my y-axis, D is 2 units away. It should be here. That should be D prime, and then C should be the further one, C prime. So let me fix that very quickly. That should be D prime, and this one should be C prime. That's sloppy. Shame on me. Anyway, back to this. Again, reflection over here. The reason why this reflection had to happen is now notice that each of these points is going to end up where it should. So now I can just, now that I've reflected it, now I can slide it down. And there's my key term, slide, because that's going to tell me what kind of transformation I can do to get there. Translation. And that tells me that if I want to get A onto E, I have to just go down 4 units. Don't have to go left or right any, just down 4. So left or right didn't change at all. So X goes to X, but Y goes down 4, and we represent that with a -4. Okay, so again, there were multiple ways I could get this object over here. Some of you might have thought, well, I can just reflect this guy, or maybe not reflect, but maybe I could start by taking this guy and sliding it down. Maybe you're thinking in terms of like, I want to line up A and B with E and F first, so I could slide this down 4 units first. So now my image is down here, and then I would just have to reflect over the y-axis. That's totally fine as well. Okay, there are multiple ways to do it. Just be careful with it, more careful than I was about labeling your points as you get there. All right, so just to finish off this video, finish off this section, finish off this unit, 2 of these properties we want to talk about. These are just kind of special case scenarios. The first of which being a reflection with parallel lines. So if I have parallel lines like K and M here, and I have reflections going over those parallel lines, so segment AB being reflected and being reflected over the next one, this is basically saying that those 2 reflections, that composition, is the exact equivalent of a single translation. And that translation moves twice the distance that those parallel lines are apart. So if these were 5 miles apart, A would be 10 miles, or twice that distance away from its image. And same thing with B. Okay. Our second one, reflections in intersecting lines. So instead of parallel lines, now what happens, they intersect in some way. They make some angle, we'll call that X. And let's say I'm still reflecting over those same lines. There's my segment. It gets reflected once over K, then reflected again over M. What this is basically saying is instead of that composition of 2 reflections, that can be described as a single rotation, where I just double that angle. So if that angle, for instance, was 25 degrees, then it would be the exact equivalent of just rotating A once 50 degrees or double what that angle was. And same thing with B.